Hello everybody, welcome to our presentation on the falling Python. Along with the falling Python and the bouncing panda, we have a new kid on the block, presenting to you the inclined plane. The movement of this green ball shall be modeled on numpy. The same shall be visualized using matplotlib, and then the interesting GIF animation that you see on the left shall be created using FuncAnimation, and the whole thing shall be packaged into a standalone GUI based on tkinter. So the tasks in this case are pretty much the same as our earlier case. This is also an example of a motion under uniform acceleration, but there's a slight twist. The force acting on the ball m into g, where m is the mass of the green ball, is acting in the vertically downward direction. This can be resolved into two components: mg cos theta perpendicular to the plane and mg sin theta parallel to the plane. The perpendicular component is to be ignored as the same is offset by normal reaction from the plane. It is a component parallel to the plane which causes acceleration of the ball. And since the force is mg sin theta and the mass of the green ball is m, the acceleration would be g sin theta. Assuming the length of the inclined plane as L, the time taken by the ball to slide to the bottom of the inclined plane would therefore be given by square root of 2L divided by g sin theta. Of course, we are assuming here that the plane is frictionless. Otherwise, normal reaction would cause friction to pop in and derail all these beautiful assumptions as above. So now let's get to the coding part. The first step is to create this red dotted circle part of the GIF image. To do so, let's look at the circle a little bit more closely. For the plane of length L inclined at an angle of theta, the dimensions marked would be as follows: L sin theta and L cos theta. This means that the red point with coordinates x and y shall have the y coordinate of L sin theta and the x coordinate of L minus L cos theta. With this preliminary, we are good to go into the coding part. %matplotlib inline ensures that the plot is displayed in the Jupyter notebook itself. We import matplotlib.pyplot as plt. We also import numpy and declare the constants of g and l. Using plt.subplots, we create a single plot with size of 2 x 2 and a resolution of 100. The x and the y axis limits are set. We draw a horizontal line using ax.axh line at y equal to 0 and color black. Then we are ready to draw the circle. The first step is that we set the radius of the circle equal to L, the length of the inclined plane. Then we generate an array. This array depicts the various angular positions. We say 100 angular positions between 0 and pi by 2 in this array angles. Then we generate the x coordinate array and the y coordinate array using the formulas that we just discussed now. Then these are plotted using ax.plot with the color red and the line style of dotted. When we run this cell, the plot, as you see, is generated. Now that we are done with generating this dotted circle, we proceed further ahead by plotting this green marker, this line representing the inclined plane, this hatching, the timestamp on the top. We notice that the line is drawn from the coordinates L, 0 to L minus L cos theta and L sin theta. With these preliminaries, we dive into the code. The code is largely the same. We add this line from matplotlib.patches import rectangle in order to create the hatching. We initialize a new constant variable angle underscore degree is equal to 30. This shall be converted to radians for further processing. We initialize this as degrees because that's more intuitive for the person using the graphical user interface that we shall be creating using tkinter. Here we have created the figure on the axis as explained earlier. This is the code for generating the dotted circle. and we initialize a line object. The reason for generating a line object is that once the line is plotted and we need to clear it during the animations, having it saved as an object makes it easier to process it. So here's theta getting converted to radians. Here is the coordinates xy, x2, y2 of this top portion where the marker is located initially for the inclined plane. Now this code ax.plot generates a line black in color with a line weight of 2, and by adding this 0 at the end of it, we are able to access the line object which has been plotted by this ax.plot command, and this line object is saved in this variable line. And as I explained this will enable us to clear the line object using a single command when we do the animations. Similarly, we use ax.annotate command to write this time at the top. So the xy basically specifies the coordinate at which the text would start, and the xy text specifies the offset. So notice that here I have given L, and this takes this time to the corner of the plot, which is not very convenient. And if I were to change it to say L by 2, then it gets shifted slightly inside. The text starts from L by 2, so you have it more conveniently placed. You can play around with this and place it where it suits you best. So this ax.fill between, this basically gives the code for doing this hatching. So we are specifying the x coordinates and the y coordinates. We are specifying the color as gray. Alpha is equal to 0.25 indicates the transparency, and the hatch / tells us the hatching will be of this type. So this marker we also created as a marker object. We use ax.plot and specify the coordinates x2 and y2 to create this marker at this coordinate, and we put this array accessing element 0 to access this marker object and save it to the variable called marker. Again, this is being done for the purpose of writing the code of the animations. So once we are done with this code, you would have a plot like this with this dotted line indicating the circle, this line representing the inclined plane, the hatches, and this green marker. So we are halfway through our project. The next step is to convert this into an animation. And for this, we would have to write the equations of motion of the marker. Now the marker is going to slide down the inclined plane, and we discussed that it would be a case of motion under uniform acceleration, and the distance moved along the plane would be given by half of at square, where a would be g sine theta. And so with this formula, we can compute the distance traveled along the inclined plane for this marker at any point of time. But notice that the entire plot is created in x and y coordinates. So we want to move from this distance s moved along the inclined plane to the x and y coordinates. To do so, we notice that s can be resolved along the x-axis as s cos theta and along the y-axis as minus s sine theta. So all we have to do is to add these two components of the x component and the y component to the initial position of the marker, and that would give the position of the marker at any instant of time. And once we know that, and we have saved this as an NumPy array, then the generation of the GIF animation using FuncAnimation is kind of elementary. So this is what we have done here. The initial y coordinate is L sine theta, and to that we have added minus sine theta, or rather subtracted. And then to the x coordinate, the x coordinate initially it's the coordinate of this top of the inclined plane. So that was L minus L cos theta, and to that we have added the value of S cos theta. So let's jump into the code. So when we are adding animation, the first thing that we do is to replace the first line to %matplotlib notebook. This enables us to display the GIF animation inside the Jupyter notebook itself. We import animation from matplotlib, and we also import the pillow writer so that we can save the animation as a GIF image. We add this variable called slow is equal to 1000. So this basically will be used to speed up or slow down the animation. So here's a code for creating the figure and the axis for the plots. We have discussed this earlier. To this we add the circle as a dotted line. Then we create the line object. We convert the angle input in degrees to radians. Then we specify the x2 and y2 coordinate of the top of the inclined plane, and this would be used to create the line. So this is the important part of the code. If line is not null, then line.remove. So what this does is that already if a plot has something drawn in it, it clears it. As I said earlier, plotting the line and saving it as a line object enables her to clear the animation in a single shot. So this is the single shot line of code which enables us to do this. So here we are plotting the line and saving the plot as a line object. Similarly, we are creating the annotation and saving it as a variable and. Now we proceed to create the animation variables. We know that the time to fall is square root of 2L divided by G into sine theta. Now we create a time array. What we have done is that we have split the time from 0 to tmax into 500 equally spaced elements. At this t display is basically the time at that particular instant. So we will have a time ticker here which is running continuously, and that we have rounded off to decimals 2. Now the distance traveled along the inclined plane is equal to half at square, and a in this case is g sine theta. The x2 and y2 coordinates of the top of the inclined plane are written, and as I just explained, we are going to add the values of x, the x component of s and the y component of s, to get the current coordinate of the marker. And once we are done with this information, this is all the information that we need to get the marker to move. This I have discussed just now. This is to create this hatching and to create the marker object at the top. So this is the magic code which gets the animation to move. We are linking the FuncAnimation to the figure, that is this figure, the update marker code which is here, and the number of frames is basically the length of this array which contains all the coordinates of the marker's positions. The interval would be the smallest time interval that we have created in this linspace array, multiplied by slow. So if we increase this slow to a much larger value, then the animation would play a lot slower, and if we reduce this value, then the animation would play much faster. Blit equal to true and save equal to count are two optional parameters. So what blit tells matplotlib is that don't create the animation from scratch each time. Just redraw the part which is different from what was there earlier. And save equal to count is really useful when you don't want to run into memory issues when creating large animations. It's really not important for this particular case. So now we go to the update marker code. So what we've done here is that we have set the marker to the updated position as per this I. So each time this iteration runs, the marker is set to an updated position from these two arrays. And dot remove, what this does is that it removes this annotation and recreates that annotation. As you can see that when we recreate this annotation, we have used Python's fstring method to make sure that the updated timestamp from this tDisplay array is picked up and displayed. And when we run this, you can see that the time is getting updated and the marker is rolling down the inclined plane. So we are almost done with the project. The last step is to add the icing on the cake, that is the tkinter wrapper to the entire code. To do this, we import tkinter as tk. Then we import ttk to add a dropdown. We use this code from matplotlib.backends import figure.canvas so that we can embed the entire code as a canvas in the tkinter window. This entire plotting part we have taken inside a function called plotLine. We have declared a few global variables so that the exchange of variables between the main part of the code and the function can happen easily. The update marker is, and this and FuncAnimation code we have discussed, we have made this a sub part of this plotLine function. And the only additions are that this canvas.draw, which ensures that the above plot gets drawn and animated in the tkinter canvas. So these are basically controls for the tkinter window, which I'll be explaining shortly. So let's come into the tkinter window. So we have created the root window. We have defined the figure and axis, drawn the dotted line, created a drop down, specified the location of the drop down, and the drop down is followed by two buttons. One button is the plot button, And this plot button links us to this plot function, which creates the plot and animates it. So we have discussed already till this canvas.draw. What these two pieces of code do is that once you have started the plotting process, the plot button should get disabled and the drop down should also get disabled, so that your PC can coolly go ahead with generating the animation without any disturbance. Then the final part is adding a reset button to reset the animation or stop the animation in case you want to do that. And what this does is it calls this reset function and it saves the animation as GIF. I've added a PLT clause so that you can have a look at this timestamp at the top for a short while. The plot is cleared by using these commands. So see here, you see the advantage of saving the plot objects as variables so that they can be removed in a single shot. You just need to write line.remove to erase the line. And it resets the line variable to none, and the canvas is again drawn to make sure that it's empty. The plot button and the drop down button are again allowed to become normal. They can be accessed again by the user. And in case the animation is still running, just make sure that the animation is stopped and the animation variable is set to none. So this is the entire code. Let's run it. So as soon as I run it, the tkinter window pops up. I click on Fortify, click on plot. You see that the animation proceeds, and here we have the timer running continuously. And when we press the reset button, it takes a little bit of while to save the GIF animation. So the code works just as we had expected. And this is the GIF image that we have created. So the final part of the project is to package all this as a standalone tkinter application. And this is done using pyinstaller. So I click on this exe file. And here's the window popping up. Let's do 60 degrees for a change. And there you go. We reset the animation. So I click on the GIF image. And there you go. So we have created one more project of creating a standalone application which models a real world physics problem, the ubiquitous inclined plane, which is there in every basic physics textbook. I hope you enjoyed the coding part as well as the physics part of it. Do like this video and subscribe to this channel. Thank you.